Thanks a lot for putting together this interesting conference. So I'm going to talk today about my work in progress on distributional policy evaluation, which is kind of part of a bigger agenda, and I'm going to present some results from that. So by way of motivations, the kind of underlying observation or conjecture, if you will, is that most interesting policy changes don't generate Pareto improvements. Usually we have winners and losers, and that's the reason why interesting policy changes are controversial, because there's some people who have something to lose from them. And so here are a couple of examples that I had in mind, starting with this project. So you can think about trade liberalization, which you can think of opposing net producers versus net consumers of goods with rising or declining prices. Say there's a classic paper by Deaton which discusses rice prices in Thailand, and as trade gets liberalized, rice farmers might be affected negatively, and slum dwellers might be affected positively. And so trade liberalization usually has that kind of effect. So a more straightforward example would be income tax reform. Say you make income taxes more progressive, that would oppose high and low income earners. If you think about changing the price of a publicly provided good, such as health or education, people are differently affected depending on whether they're marginal or inframarginal consumers of the good or non-consumers, or whether they're taxpayers financing the good. Or to labor examples, if you think about the impact of migration or barriers to migration, then those affect, of course, migrants or would-be migrants themselves, but they also affect suppliers of substitutes or complements to migrant labor in different ways. And kind of similarly, skill bias, technical change affect people differently depending whether they supply substitutes or complements to new technologies. And so if you accept this conjecture that a lot of policies generate winners and losers, and if you take the basic approach of economics that we evaluate, that we do normative evaluation of policies based on their impact on individuals, then there's a couple of questions that you have to answer. You have to answer how you would define individual gains and losses. You have to, if you want to work empirically, you have to estimate them, and then if you want to make normative statements about whether a policy change is desirable, you have to take a stance on how to aggregate individual welfare impacts to a social welfare impact. And from a more positive side, positive point of view, if you want to understand the political economy of a policy change, you might also want to understand as a first step who the winners and losers of the policy change would be, and who therefore has an interest to support or oppose the policy change. And so what I'm trying to do in this research agenda is to develop tools for distributional policy evaluation in the context of a utility-based framework. So that would be the answer to question 1.1 here, how you would define individual welfare, allowing for arbitrary heterogeneity across individuals, and allowing for endogenous prices and wages. And so kind of in a nutshell, the procedure that we're going to end up with well, the crucial step is step 1 here, imputing a money metric welfare impact of the policy change to every individual, and then using that to report disaggregated welfare effects, conditional on things like earnings, income, other covariates. And then you can use those to answer the political economy and optimal policy questions, like describing the sets of winners and losers, and aggregating with using welfare weights to social welfare impacts. And I think it's useful to keep in mind the contrast between this and the more conventional program evaluation approach, which usually evaluates policy changes in terms of just the average and of some observed outcomes. So here we have utility rather than observed outcomes, and we have possibly weighted averages or disaggregated welfare impacts rather than just averages or sums. And so what are the contributions of this paper? So here I kind of put the contrast to public finance and labor and distributional decompositions here. Some of that is a bit of a straw man. Like in all of the literatures, there are obviously people taking these things into account. But relative to like the optimal policy literature in the Merlesian tradition, here we have endogenous prices and wages. So in like the optimal income tax, optimal insurance literature, that's usually assumed away. Relative to the distributional decomposition literature, I'm looking at utility-based social welfare rather than observed income or observed wages. And relative to, I guess, more structural labor approaches that estimate demand systems for the labor market, which usually have to assume away a lot of heterogeneity and assuming things like the impact on wages, the proportional impact on wages is constant for everybody with a college degree or something like that. Whereas here, we're allowing for a very, very large degree of heterogeneity across individuals. So in terms of objects of interest, what I'm trying to push here is really reporting disaggregated welfare impacts, kind of for two reasons. First, to think about the political economy of policy changes, and second, to allow readers to have their own welfare weights, basically in order to choose how they want to aggregate the disaggregated welfare impacts into a normative evaluation of a policy change. And then in terms of formal results, so kind of the biggest formal contribution here, I guess, is in part 1, where it turns out the main technical challenge in this setting is to identify objects of this form here. So W is going to denote wage, and L is going to denote labor supply. And I'm going to use a superscript dot to denote marginal policy effects. So what this would be the causal effect of the policy on wage multiplied by the pre-policy change labor supply. So we're holding labor supply constant but changing the wage. And we want the average of that conditional on earnings. So this would kind of be the basic input into a standard social welfare function where welfare weights depend on earnings or income. And so putting this in a slightly more abstract context, the problem is to identify causal impacts of marginal policy change on a vector of endogenous outcomes, conditional on that vector of endogenous outcomes. And turns out that this problem has some close connections to physics and to fluid dynamics in particular, or more generally continuum mechanics, which might seem a bit contrived, but I'm going to talk more about that. And I think there's really a very close connection between the two. And then I probably won't have time to talk too much today about aggregation and inference, but there are some results there in terms of aggregation, mostly relating different literatures. On the one hand, kind of the public finance type social welfare literature, where we have welfare weights. On the other hand, the distributional decomposition literature. And turns out there's kind of this close formal analogy between the welfare weights in public finance and the slopes of influence functions in the decomposition literature. And if you want to kind of take your distributional decomposition as a point of departure, then you can turn that into a utilitarian welfare economic statement by subtracting some behavioral correction from a distributional decomposition effect. And then inference, nothing particularly original here, but just coming from the identification results and proposing a bunch of estimators based on local linear quantile regressions with suitable control functions and weighted averages. But that's really mostly by analogy to the identification results. And so before I get into the details, I think it's useful to emphasize the commonalities and differences here to work by Jim Heckman and co-authors, in particular as summarized in this handbook chapter. So I think the motivation of the topics discussed in the handbook chapter is very close to what I'm doing here. There's some different twists. So in terms of the first two respects, I'm less ambitious, I guess. So I'm not going to talk about the distribution of treatment effects, conditional and covariate, say, for a discrete treatment. I'm going to want something a bit more peculiar than that. I'm just going to want some conditional average causal effect, conditional outcomes. So that's more special than having the entire distribution of treatment effects. And also, I'm only going to do this for marginal policy changes rather than discrete changes of treatment. Second, even though I'm interested in general equilibrium effects, I'm not going to get into the business of predicting general equilibrium effects of counterfactual policies. Mostly what I'm going to do is essentially have the form of some kind of ex post evaluation of policy changes that took place. And in the third respect, maybe slightly more ambitious, looking at equivalent variation rather than impacts of unobserved outcomes. So I'm not going to get into, I mean, there's a whole lot of other literature that's relevant, but in the interest of time, I'm going to skip that. Here's the notation I'm going to use throughout. So there's always going to be a policy alpha, or indexed by a parameter alpha. So you can think of a tax rate or a tariff or any parameter really indexing a set of policies. There are going to be individuals I. Superscript alpha is going to denote potential outcomes under policy alpha. So W alpha is the wage you would get if policy alpha was implemented. W is the realized wage. Partial derivatives, usual notation. And then, as I said, I'm going to use derivatives with respect to the policy alpha all the time. And so those are going to be denoted by a superscript dot. So W dot is the marginal effect of a policy change on your wage. Densities are going to be lowercase f, cumulative distribution functions are uppercase, quantile functions q. And I'm going to focus on a static labor supply model for specificity, where we have a wage W, labor supply L, a consumption vector C, taxes T, and covariates W. And so here would be the kind of a conventional static labor supply model, where individuals maximize utility through choice of consumption and labor supply, subject to a budget constraint which involves earnings, so L times W, net of some taxes on income, and plus possibly some unearned income. And the value function of this problem is denoted V, so that's the maximum of utility subject to the constraint. And so I want to emphasize that pretty much the entire logic of what I'm going to talk about is going to hold under much more general conditions. So it holds under additional constraints, informational constraints, dynamic settings, and so on. Basically, the crucial feature that I'm going to need is that some envelope condition holds. Yeah, so, but this allows me to be more explicit about what I'm doing. And so one thing I want to emphasize here is that I'm allowing for arbitrary heterogeneity. So utility and wages and therefore consumption and labor supply all can be should be thought of as indexed by I. And policy can affect anything here. So it can affect prices, wages, unearned income, taxes, and therefore again consumption, labor supply, and realized utility. But as usual, I'm assuming that preferences are invariant under policy changes. And yeah, just satisfying the usual conditions. And so with this model at hand, we can define more explicitly the object of interest that I want to talk about. It's kind of the basic unit here is the equivalent variation of the marginal policy change, so E dot. That's the impact of the policy on realized utility, normalized by the marginal value of unearned income. So it's just equivalent variation or compensating variation, which are the same for a marginal change, right? It's just putting everything in dollar terms. And based on that, we can then define the objects I talked about. So first, those disaggregated average welfare impacts, gamma, which is the average welfare impact conditional on your income and exogenous covariates. And then based on that, we can talk about sets of winners and losers in expectation. So I guess winners and losers in expectation conditional on Y and W. And we can talk, so that's kind of would be the input for a discussion of political economy here. And we can talk about social welfare, which would be a weighted average of gamma, at least under the condition that welfare weights depend on Y and W only. And now let's start with the first one. So let's talk about the E dot, the equivalent variation of the policy change, and the impact of the policy change on income. So this would just be the right-hand side of the budget constraint. And the first one is just differentiation, right? So the impact on income you can write as an impact on labor supply, an impact on wages, an impact of tax change, and an impact on unearned income. And whereas the equivalent variation is almost the same, except the behavioral effect drops out. So that's the envelope condition. And so that's really I would argue, kind of the main normative implication of being utilitarian is essentially you don't care how people change the behavior when you change the policy. Those terms drop out at the margin. That's really what it means to be utilitarian. However people change the labor supply in response to the policy change, we don't care as far as their own welfare is concerned. We might care through its general equilibrium effects and through its effect on public revenue, but not in terms of the effect on the individuals themselves. And then on the other hand, in addition to the terms for income, we have the price effect here too. And so the difference between the impact on income and the equivalent variation has those two terms. One is the labor supply or behavioral effect, and the other one is the price effect. Just to fix ideas with an example that I want to talk about again later in the application. If you think of the expansion of the earned income tax credit in the 90s, so essentially that made welfare payments or public transfers for poor mothers contingent on having labor income, right? So when you think about the various impacts that might have, so there might be a mechanical impact, at least if you compare it to unconditional payments, it's positive for the working poor and negative for the unemployed poor. There is a labor supply effect, which is positive in the sense of, it has been documented a lot, that the increased labor supply, and then arguably, Jesse Rothstein has made the argument, and I'm going to find it too, there's a negative wage impact through the increased labor supply. And that's actually negative for both mothers and non-mothers, where non-mothers are not eligible for the EITC. And so if you compare kind of different stylized ways of evaluating this change, so the prototypical labor approach, I would argue, would evaluate the policy change in terms of realized income and say, oh, it's great because there's a positive mechanical impact. And there's kind of the increase in labor supply, and then you might want to subtract the wage impact. But from the perspective that you just look at income, it's a good thing that labor supply is increased, right? From a public finance perspective, or the way it's usually evaluated in release type models, you have the mechanical impact, which is just the mechanical incidence of the policy change. And kind of assuming away price effects, that's it, because we would ignore the behavioral effect, except to the extent that it generally generates dead weight loss in the presence of negative marginal taxes. And in terms of kind of the setting that I'm proposing here, there would be the mechanical wage impact. But from that perspective, the whole thing looks worse than from the perspective of both the utility with fixed wages perspective and from the income perspective, because there's a negative wage impact and we don't count the positive labor supply impact. So I'm going to get back to that at the end of the talk if I have time. OK, so now, as I said, in terms of the object of interest here, right, so the basic object is the E dot. We just wrote down what it is in the context of the labor supply model. And then based on that, we want to characterize or identify the object gamma here, which is the conditional average welfare impact given income and covariates. So we want to identify this gamma, which is the expectation of E dot given Y and big W. So I have to apologize for the reuse of letters. Big W is just covariates, little w is the wage. But when you combine a bunch of literatures, you soon run out of letters. And OK, so and then to make my life simpler, I'm kind of going to consider the simplest baseline case, ignoring changes in taxes, in prices, in unearned income, and just going to focus on the effect of changes in wages. So what I want then is basically the expectation of labor supply times the change in wage. So that was this first component here, right? I'm ignoring the other terms here, just focusing on the impact of changing wages. And we want that conditional on earnings. So, and since both labor supply and wage are going to be endogenous to the policy, what we need is essentially, if you denote the vector labor supply and wage as x, what we need is the causal impact of the policy on the vector x, but conditional on the vector x, since we want this disaggregated conditional on earnings. And so the kind of here, putting this problem now in the more abstract framework, what we want is the expectation of x dot given x and alpha, where x would be labor supply and wages, for instance. And we want to learn that from a density of x given alpha. So here, I'm kind of jumping ahead and already assuming that I essentially know the marginal distribution of potential outcomes. So we've solved all the usual program evaluation problem. And really, kind of to jump through these hoops, that's made necessary by a combination of two things here. The combination of looking at utility-based social welfare rather than welfare evaluated in terms of some observed outcome. And second, by the fact that we have heterogeneous wage responses, right? So you can take the entirely same framework and say, look at the price of rice and how it impacts people. We wouldn't have to do that because there's just one causal impact on rice, which is the same for everybody, and we would just have to take, basically, find out what everybody's net consumption of rice is and multiply that, and we're done. So it's really the combination of having utility-based evaluation where we don't want to count behavioral effects, but at the same time allowing for heterogeneous wage responses. So that's something that would be relevant in other heterogeneous markets, like, for instance, real estate as well. OK, so here's the framework I'm going to talk about for the next bunch of slides. Kind of in a nutshell, assumption would be there is some structural function x, which maps the policy level and unobserved heterogeneity epsilon into realized outcomes x. I'm assuming the perfect experiment with alpha independent of epsilon. So a different way of saying that is I just assume that we know the distribution of potential outcomes, or the marginal distribution of potential outcomes. And just to make my life easier, I'm going to assume that the structural functions are differentiable. That one is not strictly necessary, but
X is epsilon scalar?
No, it's not. Epsilon can be anything, so can be infinite dimensional. So essentially, instead of epsilon, you could write I. Everybody has a different function x of alpha and I. And now if we take the framework in this way, there is a physics analogy that I mentioned in the beginning, where...
So you're looking at very special policies that are random, basically?
No, so here, this is kind of just to fix ideas. So in the application, I'm going to get a setting where essentially it's going to be a difference in difference type identification. The point is, we have in some way we have identified the marginal distribution of policy of potential outcomes under different policy levels, and so the conceptual baseline would be the experiment, but not necessarily the most relevant one in practice. Yeah. So physics analogy. So we could think of x as describing the trajectories or orbits or paths of a particle over time. So where now you would think of alpha as time and epsilon as just indexing particles. And the density, the probabilistic density of x given alpha, that would now correspond to just the physical density of a gas at time alpha and position x in space. F dot would then be the change of the density at that point in time and space over time. And finally, I'm going to use this notation here, which is going to be useful, this function h, which is essentially the object that we want to learn about, so this conditional causal effect, but then rescaled by the density. So this is just going to make the formulas look much nicer. And this is what the physicists call flow density.
Whenever it's convenient, can you give us some intuition of why this is useful in a social science context where the variation in the data is the EITC was one level, and then we changed it by 15% and changed the cutoff by $5,000. So we're usually in these policy things having big discrete changes rather than continuous changes.
So here's the variation I'm going to use for the EITC, which is the state top-ups in the EITC level. I mean, I guess the point of the slide is going to be just to show there's a lot of variation, right? So anywhere between a 0 top-up, 4%, 5%, 8.5%, 10%. So there's a lot of variation there that I'm going to exploit. Of course, in many practical circumstances, this is going to be an issue, and we have to somehow deal with interpolation, which I would argue is not particular to this problem, but yes. If you're willing to impose some form of functional form restrictions or heterogeneity restrictions, that's going to allow you to take care of these interpolation issues. If not, then you're doomed, I guess. But I'm going to assume that we do have this available and take this as my point of departure. And kind of the physics analogy of my question then would be, if we know these densities fx given alpha for different points in time alpha, what does that tell us about the underlying flow? And when you put it in these terms, you can start seeing where the problem might come from. So for instance, if you stir your coffee, turns out that water is incompressible, so the density does not change over time. And so is coffee, or whichever your favorite beverage is. So if you stir the coffee, you don't change the density of coffee, but you do generate flows that are not equal to 0. So that means there's different flows which are consistent with the same marginal densities fx given alpha. So that's going to tell you that there's an identification problem here. And turns out that this analogy is actually going to be fairly informative, and I'm going to come back to it. So the results I'm going to have on the next couple of slides are going to be first, if we know these densities fx given alpha, then this identifies what's called the divergence of the flow density h. So the divergence is taking h, which is a vector field, right? So for every point x, it tells you a vector of directions of the kind of net average flow of particles at that point, or equivalently the average causal effect conditional on that point. And the divergence is taking each component of h, taking the derivative with respect to the corresponding component of x, and summing up across components. Without further restrictions, knowing the marginal densities don't identify anything else. And another way of saying that is that if we add an arbitrary h tilde to our flow, where h tilde has a 0 divergence, then that's not going to change the observed densities. So that's exactly the stirring your coffee type h tildes. So the incompressible flows, or the flows that don't change the density, are exactly the flows that have a 0 divergence. But if you are willing to impose additional restrictions of heterogeneity, or exclusion restrictions, if you will, such as in the context of the application, for instance, something like the average wage response, conditional on wage and covariates, does not depend on initial labor supply. If you're willing to impose that type of restriction, you can think of it as some kind of triangularity restriction, then that's exactly the condition that gives you a just identification of this object, and it's going to be just identified by quantile regressions with control functions. So this is the first result. Just to recap notation, H is the flow density, so the conditional average causal impact multiplied by the density. Nabla times H is the divergence of this flow, and F dot is the change of the density over time or across policy levels. And now the first result, which I guess in different contexts is well known, is that the change of the density is equal to minus the divergence. And so if your kind of intuition here would be, say we look at the first dimension and we look at this little square and we want to know how much the mass in this square changes over time or over policy levels, then we have kind of an outflow here to the right and inflow to the left, and the difference between them is going to determine what's the change in the density here, and the same for the outflow to the top and the outflow to the bottom. And so that this difference would be basically the first component of the divergence, and then this difference would be the second component of the divergence. And so here's the proof of that. That's the only proof I put in the slides. But I think this is useful in various contexts, so the kind of logic. So I wanted to do it. So take an arbitrary function A that's smooth and has bounded support, and look at the expectation of A of x conditional on alpha, and we're going to note that big A of alpha. Then you can write that in two ways. You can write it as an integral over underlying heterogeneity epsilon of A of x of alpha epsilon, or you can write it as just an integral over the distribution of x conditional on alpha, right? So that's just using a different kind of domain of integration for the same object. But now when you take those two representations and you take the derivative in each representation, so 2 would be the first one. Sorry, does this work? Yeah. So this one here, that's what you use for this derivative, and then this one on the bottom. So for the first one, if you take the derivative and you pass your differential under the integrals, you get this here, this expression here, and then when you take that and you do partial integrations, then you're going to end up on the bottom line here, but that immediately gives you an integral of A times the divergence of H. On the other hand, if you take the second representation where you integrate AX over the distribution of x given alpha, you're going to just, again, passing the derivative under the integral, you're going to end up with integral A times F dot. And since you can do that for any smooth function A with bounded support, this tells you that F dot has to be equal to minus the divergence. Now, okay, so what this tells you is if you observe the density F, then you have the divergence of H identified. The question is, do we learn anything else about H? Next theorem tells you no, without further restrictions. And so the way this theorem is stated, I'm giving you one function H naught, which satisfies, which is consistent with the density. So H naught exactly has the form that I mentioned before, where it's a quantile regression with control functions. And then we have the set script H, which is the set of all little h tilde that have zero divergence. So this says the identified set is the set of all functions which correspond to this particular function, which is consistent with the data, and then adding an arbitrary function with zero divergence to that. Right? So you can think of script H as like the kernel of the identified set. Now the question is, how does this script H look like? Turns out in one dimension, it's actually just a trivial function 0. So in one dimension, we are actually point identified. So I thought this was a nice result, and I think it's still a thing it is, but this actually is Hoderlein and Mammen, 2009 or something, 7. So we get the conditional average causal effect for a one-dimensional outcome just by doing the quantile regression. So in that case, this function H naught, there's not going to be any control function because there's no other components of the outcome vector. In 2 dimensions, this kind of the kernel of non-identification script H has this form here, which is actually kind of neat, I think. So it's given by the set of all function H tilde that you get by taking an arbitrary function capital H, taking the gradient of that and then rotating it by 90 degrees. So it's basically you take like an arbitrary landscape of mountains and valleys, and you always walk around lines of equal height in this landscape. And that's exactly the type of flows that you can get that satisfy, that they have zero divergence. And that's exactly the kind of flows you get when you stir your coffee. So here would be a picture corresponding to that, just taking an arbitrary function with one valley and one mountain, and then the corresponding flow that you get from that is just walking around the lines of equal height in this landscape. And this doesn't change the density, right? Because if you look at any small area here, there's as much inflow as outflow. But so that's nice, but not useful for my problem because I really have labor supply and wage being endogenous. So I have to deal with the two-dimensional case in particular, or in more complicated settings with a higher dimensional case. So you can do similar characterizations for arbitrary dimensions. They just get messier. So for 3 dimensions, you get the set of all functions h tilde that are given by what's called the curl of a vector field G. And now here's the point identification result. If you're willing to assume a restriction of this form, that the conditional causal impact on xi, given x and alpha, does not depend on xj for j with indices higher than I for some ordering of the components of x, that type of exclusion restriction or that type of restriction of heterogeneity is exactly what you need to get point identification. And if you're imposing that condition, then you get kind of the same form for G for higher dimensions and not just for the one-dimensional case. If you don't get it, impose something of that form, you don't get identification. Yeah, so you have to somehow restrict heterogeneity a bit to get what you want here. Talk very briefly about aggregation. So as I said, there's kind of part of the motivation for this project came from thinking about the relationship between the distributional decomposition literature and the public finance social welfare literature. And I have some results characterizing the connection here. So the first one would be this theorem which says that if you look at the impact of the policy change on either social welfare, which is a function of realized utilities, or in some statistics theta, which is a function of realized incomes, you can, one way to think about them is just as weighted averages of the individual impacts, where here the omegas would be something like welfare weights. But another way of thinking about that, and this is one that's become popular in the distributional decomposition literature, you can think of theta as a function just of the distribution of y's, and then we have this influence function representation, or I guess as Fipro-Fortin and Lemieux called in their paper, with regression representation of this impact. And if you compare those two representations, it turns out that the influence function of the statistics theta and taking the slope of that with respect to y, that's formally analogous to the welfare weights of public finance. I'm going to skip the other stuff. So as far as estimators go, kind of by analogy from the identification results, if you're willing to impose this type of exclusion or triangularity restrictions, so basically it's going to be a combination of kernel estimators of conditional CDF and local linear quantile regressions, and then taking averages. So in the interest of time, I'm going to skip that. So I can get a bit to talk about the application, which, as I said, is going to be about the earned income tax credit. In terms of the identification approach, I'm just following a paper by Lee, 2010, which uses this state-level variation in state top-ups for the earned income tax credit across time and states. And the data used are just the current population survey, March outgoing rotation group data, and the definition of alpha here, which turns out to be fine, since pretty much the set of EITC schedules is kind of a one-dimensional family, is the maximum EITC benefit available. So here's the variation that I showed before, just to illustrate there's quite a bit of variation across time and states in terms of the EITC top-ups that states provide beyond the federal EITC. This is reproducing the results by Lee, so it's kind of, this shows that there's something there which motivates that this analysis is interesting. So if you look at the impact of the estimated impact based on this variation of the EITC, you get a fairly negative wage impact for high school dropouts, a moderate wage impact for the high school diploma-only people, and basically a zero impact for the college graduates. And this kind of parallels the impact on employment. So what's kind of interesting here is that the wage effects, conditional on the employment effects, seem reasonable, so they kind of line up with standard levels of elasticity of labor demand. What's kind of surprising is that the employment effect is so large given these wage effects. but it is what it is. I'm just using this variation now and applying my approach of going from these causal effects on the distribution of wages and labor supply to these welfare impacts. So here would be what I would get just for a random sample of 1,000 households from the data, the imputed welfare impacts. And so here you kind of see that the people with zero annual earnings, they're not impacted. It's just mechanically, because if you don't have any earnings, the negative wage impact is not going to affect you much. Then you have kind of the working poor range here of like 20,000, 30,000 a year. They're quite negatively impacted. And then once you get to 40, 50,000, the average effect goes to zero, which is kind of what you would expect from the logic of the policy change. Now, if you just look at high school dropouts, it looks quite a bit worse. So just notice here the scales are different a bit, right? So here your high school dropouts are affected quite a bit more adversely. And here would be just a kernel regression of these welfare impacts now for the entire sample rather than for random subsamples. And here you have kind of this U shape of the impact for everybody, a more negative impact for the high school graduates, and even more negative impact for the high school dropouts. So what's a bit weird here is that these effects don't actually kind of vanish when you go up in the income distribution. All those policy changes, all the states decided to provide top-ups to the federal EITC. So they provided additional subsidies of low earnings, just proportional to the federal subsidies. And this is the percentage amount that they provided in terms of top-up to the federal amount. So basic motivation for this research agenda is most policies generate winners and losers. If you accept this premise, then you should be interested in disaggregated welfare effects, which can then be used to discuss political economy in terms of sets of winners and losers, and to discuss optimal policy in terms of weighted averages of these disaggregated welfare impacts. The framework I discussed allowed for endogenous prices and wages, defined individual welfare in terms of utility or equivalent variation, and allowed for a large degree of heterogeneity across individuals. And the main kind of technical challenge is identification of those conditional causal impacts on vectors of endogenous outcomes, such as labor supply and wages, and possibly other dimensions of behavior and other market prices. And I'm going to leave it at that. Thanks.
Let me discuss this paper, which is a very ambitious paper. And if these slides look familiar, they should, because actually Max sent me his slides yesterday, and I wrote some notes on them. So I'm going to just show my notes on Max's slides. This paper has many moving parts. And I don't know if an hour would give it enough time, maybe a day, a week, because it has many different claims and many different goals in the paper. And let me just summarize those briefly. And that is that he's looking at point or set identification of expected individual welfare gains. That's the interesting part, conditional on certain choice variables. This is the point that came up already in the discussion. And he wants to use those individual welfare gains to look at the distribution of welfare effects. Correct me if I'm wrong at any point. These are your slides. Well, these aren't your slides. I added this to yours. And what's interesting is that he doesn't have any restriction on the dimension of the heterogeneity, at least at the beginning of the paper. It starts getting a little more restrictive towards the end, I think. And then he's using aggregation over a population using the social welfare function, and points out a relationship there between that and standard influence functions. And you do have GE effects. I think at the end you were talking about a general equilibrium effect where wages were depressed as people were entering the market. And you look at the study impact of EITC. So I would just raise a few key questions, and I would just say some of these are key assumptions to the analysis. First of all, I think it was kind of passed over, but I don't know if people were aware that alpha was a scalar. And that's pretty important, that alpha is a scalar so far in what you have, right? Because in place of the alpha scalar, you would have like alpha vector, and you'd get a bunch of partial differential equations. And that could be a little more complicated. But anyway, we'll come back to that. And then differentiability is assumed strongly. That already came up in the discussion. And then there's some support conditions that were made. And I don't know if I'll have a chance. Let me just talk. Since Chris is here, I thought I'd advertise some old work that we did together. And just saying the importance of general equilibrium. And again, if you look at the wage effects here at the bottom of this paper, when you allow for general equilibrium effects, you do get substantial impacts. And that's also true even in the work that Duflo did. Even in the paper that was discussed previously, there was a general equilibrium effect, and she did actually compute a later model and found that those were substantial, and they modified somewhat her conclusions of the paper that was discussed in the first session. So let me just place the paper a little bit. It didn't get a lot of motivation, but let me just lay out on a standard model and where this fits in the model. So the standard treatment effect model, which we heard a lot of the first paper, is a two-outcome model. We only observe one coordinate. A person gets treatment using D as the notation that was also used in the first notation. We observe Y. And then we have these two problems, which are really being addressed in this paper, but in a special way. The first is that we actually only observe conditional distributions, and we have to solve the selection problem. And then we want to construct joint distributions over these to consider counterfactual gains. And we know the standard reasons for looking at joint distributions. There are a lot of interesting questions that might rise out. Welfare criteria, like percentage of people voting, gains to poor people in the base state if you're a Rawlsian. And so the solutions in the literature, the three really kinds of solution. One is to create bounds. Verchet bounds or Makarov bounds have been put in the literature. There's earlier work by Peterson and the kind of a Roy model, a competing risks model, and a huge literature has actually emerged from that. There's also solutions that postulate dependence about these Y0 and Y1, and then solutions that are based on agent participation rules and choice data. And you're actually using the choice data somewhat in this paper. So these are the standard kinds of bounds. And there's also matching, which is also used in the paper in the sense that we're conditioning on some match variables that give us independence. And if all the dependence and the copula is captured through these Q matching variables, we can construct the joint distribution. Common coefficient model, standard assumption, and then quantile treatment effects, of which we heard. And we know that those kind of beg the question about the true case of heterogeneous treatment effects. And other assumptions have been put in the literature, and I won't. And then the Roy model, which was also mentioned in the first paper. And then models are supplemented with various kinds of assumptions about modeling choice behavior, as well as imposing dependence in the structures between choice and outcome equations. Now, if you want to think about the paper today, we can think of YD subscripted as being on a continuum, right? And so what we have is a continuum, and the different policy states are essentially characterized by alpha, which are different states of in his case, the EITC. Now, what's different, and different from the standard model, is across the different policy states, there are no new unobservables. And so in this case, it's not like we introduce some kind of unpleasantness, like welfare stigma or something, right, that might arise if you suddenly introduce, like even in a local case where it locally perturb EITC away from a boundary. So that's an interesting, that's a restriction, and that's kind of implicit. So this is literally, now this is where we start getting on familiar ground, because I'm using your slides and just putting some questions. So these are his slides. You can read them again because you saw them already once. And I will, and these are essentially the strategy. So the key point is to try to identify these conditional expectations and to try to look at welfare gains. And then inference, later on in the paper, you skipped over this really quickly. You didn't really cover it. Is looking at local linear quantile regressions, control functions, combinations of these strategies, and forming suitable weighted averages. So there's the utility function. And then we identify a set of winners and losers, where Y is basically a set of outcomes, and cap W is a set of conditioning variables that aren't affected by the policy, right? And so we want to identify this set of winners and losers to do the political economy or for setting up social welfare functions. So I guess the first question I would have is exactly how do we characterize these gamma? If you go back, I'm going to gamma, and actually I added one thing to your slide. I define gamma here, is basically this conditional expectation. And so the question becomes, how am I treating this heterogeneity? Heterogeneity in the paper is introduced somewhat late in the game in terms of epsilon. And we would think that even for a given set of observable Y and W, we'd still have some gainers and some losers. So I wasn't exactly sure. And especially if I go back to this other literature, thinking about the distributions of gains and losses, I would actually think I would need much more than the conditional expectation. So the goal is to identify this object here And just to take a simple case, and this is the case that he had. This is his definition of gamma y. I've got to go quickly. And Z is basically just labor income. So notation kept switching around in your slides and certainly in the paper. But you want to identify this object here. And so that's the goal of the paper. So what do we really know about this? So the initial stage of the paper started off with a little bit of misleading introduction. It kind of introduced the apparatus that you would really know f of x given alpha. So this is really basically a continuum of random assignments, right, across the strategy. But that's okay, it's just a thought process. And so it's really saying that what you know is you've settled the question which dominates even the first paper and much of the literature. How do I estimate this? You later address that, but using methods that are somewhat more conventional. I think that's a fair characterization. But actually, if we knew f of x alpha, then a lot of questions of a policy evaluation could easily be estimated, right? Because you would know everything. Because x basically, remember, is wages and labor supply. Then these are his assumptions, and this is the differentiability, and the epsilon is explicitly introduced. And here's the fluid flow. Very nice. I took undergraduate physics, and I hadn't seen it in a while. Nor had I seen Green's theorem or Stokes' theorem for a while, so it's very nice to see it used in economics. And so here's the idea, is that, no, but it's a very interesting idea, because what he's saying is that you know this f of x alpha. That's knowing the data. Then you can identify this divergence. And the question is, you can characterize the solution that this divergence would have. So the h function is defined up here in terms of, we know f, xa. We want to, and h is essentially the object we want to know, or really the object to the first object to the right is the object we want to know. And we can then ask, how can we find unique h? And finding unique h is like finding the first term that's unique, given f of x given alpha, and assuming we have non-zero densities. So the point is that he's able to characterize the just identified set, or the identified set, as basically the solutions to this equation. That's the set of solutions. And so that's his equation. That's a very interesting, and I think it's a useful result. And this relationship is really a property of differentiability, per se, right? And so when you talk about, the question is, can you gain additional restrictions from properties of the expenditure functions and the utility function? That wasn't actually used. There are things like quasi-concavity. There are different properties that might be used in addition to narrow that. And it wasn't clear how your framework would allow me to actually introduce some additional restrictions and possibly narrow down the set of just identified, of the set of identified equations. So this is the theorem that we heard. But then I would simply say we're solving this equation. And then the question is, what do we do about boundary conditions, identical conditions? That's a standard issue, right, in fluid mechanics and fluid dynamics. But it would show up here, I think, too, because we're looking at this as a differential equation. We want to ask whether or not we're able to do anything. Now, what he's doing in one thing, and here I'd relate it to some of the literature, and I think it would be useful in the paper to relate it to the existing literature. He was using a kind of triangularity assumption, as far as I understand it. And namely, this theorem 8, which you saw already, that's his theorem. He put in, he has this relationship of g with the derivatives of these quantile functions. In terms of he wrote in terms of x, but that's really what this is. And there was an implicit assumption of triangularity, which seemed very similar to what was going on in Blundell and Matzkin. A paper was just published, I think, this summer. And so they take it to a point that I thought Derek was about to get to, but didn't quite, but I'll make it. And that is multiple component policies. If we think about the EITC, it really is described not as a single policy. It's not like a proportional tax rate. It's actually a whole schedule. And because of it, we're actually imposing that. And so the idea was, do these results generalize to a more general kind of policy analysis? I think it's possible, but I didn't work it through. And I would just ask you that question. And now the standard strategy, of course, first of all, is the question of, do we get a well-defined PDE type result out when you think about what the real EITC is? It's putting in lots of different perturbations. And then we can convert to an ODE, and of course we know that in solving PDEs we can use a so-called method of characteristics curves, which is well developed for certain classes of these. But anyway, it's an open question as to how we'd go about doing it. So I think the multiple policy extension could really be very fruitful. So the aggregation result you didn't discuss, and I won't discuss, and it's an interesting link with the social welfare function and the influence function. I think that's interesting. This is also what his estimate is. This is the individual estimate of welfare gain. And then the question would be, suppose that we imagine the social welfare function depending on x. Suppose we thought we had characteristics, that we're weighting people for special characteristics. So we have the characteristics of the individual entry. X could be things like income. I want to help the poor. I'm going to give myself an extra welfare weight. And how would your analysis generalize in that case? Maybe it's an easy case. I wasn't able to work through it. Here I'll give some advertisement here for Sir Richard, who's sitting in the back, and simply ask Max the question of how you would relate this to this other paper, which I think is actually very interesting. I had the good fortune of spending some of the summer with Rosa in several venues, and we actually worked through this paper. I don't think the paper is actually written yet, is it? So I just have the slides. So anyway, the point is that it's an interesting contrast, because instead of the high dimensionality which they're using, they actually impose kind of a very strong condition of sort of the number of unobservables is the same as the number of endogenous variables. But then what do you get out of that? And that's the question. Of course, you can add a lot of unobservables just additively, and it's essentially it's the important intrinsic rank of those unobservables, not just the number of unobservables. So anyway, so here you have a system of demand equations, non-parametric, and you have some conditioning variables, and then you can invert and come out and solve and compute individual welfare effects. It would be interesting to compare what you're doing with that, because you would argue, I guess, that you're not having to make these strong multidimensionality. You can allow for arbitrary. I guess you would be claiming you can handle the case where this g could be of arbitrary dimension, the epsilon g, and here it's fixed. And that would be a great relaxation of the straitjacket if you could do that. I just didn't see exactly that relationship. So invertibility. So let me just conclude. This is my -1 minute. This is the last slide, really. Well, no, a couple of the last slides. First of all, many reforms are not captured by scalar alpha, and there are multiple margins. Secondly, I make a point about the last piece of empirical work, which is really very interesting, showing that actually the EITC expands labor force participation and depresses the wages of the people who get it covered. So that's an interesting point. And that actually was going on in Indonesia too, something like that, as people got into higher school levels of schooling. But I would also point out an alternative story. And so let me just first of all show you what an EIT schedule looks like. And the question is, most of the changes in policy are various shapes of this trapezoid moving all around. That's the first point. And secondly, I'd point out that some other work that I did with Lochner, we actually looked at EITC, and it turns out, of course, that EITC has other effects as well. And it turns to have effects on skill accumulation. So if you write down a human capital model, whether it's a learning by doing model or a model of on-the-job training, but by changing the margin of people at different levels, you're actually in some branches of this function actually making it cheaper to invest, like in an OJT model, or making it more expensive in a learning by doing model. These two have opposite implications. And you basically then get, can get skill acquisition effects, which would then have additional effects. Sometimes you reduce skills, sometimes it really depends. I just took some figures out of our paper where you actually can look at wage effects. And you actually find that there are actually, where you get crossover effects at different levels of the distribution. So I would be a little cautious about the general equilibrium effect that you're finding. I think the whole EITC literature kind of ignores the fact that there are some important skill incentive effects that arise. Having people have less human capital, say, would actually then lead to what looks like lower wages and like a general equilibrium effect. So two questions. One would be accounting for that, and secondly, can you accommodate that kind of generality in your model? It would be very useful if you could do so. But I do think it's a very ambitious paper. I really enjoyed, I did enjoy reading it. I hadn't read Stokes' theorem in years, and Green-Stokes' theorem, and I really thought it was done in a very interesting way, and was extremely ambitious. So I laud him for ambition. Okay, thank you.